Hi everyone, welcome to the 8th module of this course on microsensors and nanosensors. We are discussing tactile and pressure sensors. This is the third lecture in this module. In the first two lectures we have discussed about tactile sensors, but we have not yet discussed anything on pressure sensor. In our seventh module, we have discussed about force sensors in detail. So we will be utilizing the concepts of all these sensors that we have studied related to force and displacements in understanding a pressure sensor. Okay. So what we are going to essentially discuss in next three classes are how the physical pressures are converted into electrical signals. Okay. And its application is tremendous, including in healthcares, automotives, aerospace, and in the industrial automation. Okay, these are some limited application that I have mentioned, but of course the application is tremendous, particularly where we are dealing with fluids, including liquids as well as gases. Okay. If you remember the concepts of direct sensors and complex sensors from our first module of discussion, you can understand that these pressure sensors can be classified under the complex sensors. Okay, this is because some multiple steps of energy conversion are required before a pressure can ultimately be transformed into some electrical signal. Okay, so mostly these pressure sensors are, depending on what type it is, they are classified under complex sensors. Okay, the working principle of most of the pressure sensors that we are going to discuss is based on converting the impact of pressure applied to a sensitive element into electrical signal. Okay, particularly in terms of force, but you should be very careful that when you talk about this force sensor and you try to dig out the pressure sensor out of it, you should be very careful regarding the specific surface area where this force is applied. Okay, because otherwise it is very difficult to derive the pressure quantity out of this force applied. Okay, particularly what I am talking is more relevant into a liquid system or a fluid system or even a gaseous system. Okay, so when you apply the pressure, the element, the receptor where you are applying becomes displaced. Okay, it changes its position, or it can be deformed as well. Okay, because of the applied pressure. Okay, so as a result, a pressure can be a measurement of the deformation or the displacement. Okay, so this displacement can again be related to the force, and we can calculate the pressure applied based on the specific area where this force has been applied, if the specific area is known to us. Okay, so you know that I am talking about this fluids regularly, right? So you should be knowing that the matter can be classified into mostly solids and fluids. That fluid contains both liquid as well as gases, right? So however, the distinction between these liquids and gases, particularly for the pressure applied, is not quite definite. So by adjusting the pressure, liquids can be converted to gases as well as gas can be converted to liquids, and the most regular example that we can give is the LPG cylinders that we are using in our household. Okay, the gas has been pressurized to convert it into liquid. Okay, so that's how we liquefied the gases. So what I want to say is, by adjusting the pressure, liquids can be converted to gases, and again gas can be converted to liquids. Okay, so in a fluid, pressure is always applied to normal to the surface. Please remember that it cannot be directed in any other direction. At any angle, if you want to deviate from 90 degree, okay, fluid will just slide over or it will just flow. Okay, so mostly what we are going to discuss in this course or in this next three lectures is the pressure that is applied to fluids, and that is of course normal to the surface. Okay, so any force that is applied to fluid acts actually tangentially. So while the pressure exerted on the boundaries is actually perpendicular to the surface. Okay. So if I talk about a fluid which is at rest, pressure is defined as the perpendicular force F that is applied per unit area A of the boundary surface. Okay. So if I talk in terms of force applied, so pressure can be given as the change in the force divided by the area. Okay. So pressure is strongly influenced by the position within the boundaries. Okay. So at a particular position, it is quite independent of the direction. Okay. So consider a balloon where I have trapped some liquid molecules. Okay. Some liquid molecules has been trapped in this. Okay. All these molecules is exerting pressure at the boundaries. What I want to say is the pressure is, the applied pressure is strongly influenced by the position within the boundaries. Okay. So at a particular position, actually if I talk about any position, it is independent of the direction. Okay. So the pressure at a certain depth in a fluid of say uniform density is the sum of the atmospheric pressure and the pressure which is resulting from the weight of the fluid itself. Okay. So mathematically if I want to express this, I can say that the pressure exerted is equal to P naught plus rho GH. Okay. So what I am saying is the pressure at certain depth in a fluid of uniform density is the sum of the atmospheric pressure. Okay. So this, in this equation, this is the P naught is the atmospheric pressure and the pressure which is resulting from the fluid's weight. Okay. So this rho GH, okay, where this P is the pressure at particular depth, P naught is the pressure of the atmosphere, rho is the density of the fluid, G is the acceleration due to gravity and H is the depth inside the liquid. Please note that in this equation what I am considering is the uniform density of the liquid. Okay. If the density is not uniform, this equation will no longer be valid. Okay. So we are trying to understand pressure from different angles, to actually develop a pressure sensor. So mostly in today's class, I will be talking about different angles of understanding this concept of pressure. Then only we will move to the actual sensor fabrication and its application. Okay. So please note that as I have mentioned earlier also, pressure is not influenced by the shape of the confined boundaries. So the confining boundaries shape is not actually influencing the pressure. So what it means that it gives you an opportunity to develop different size and different shape pressure sensors because it is not influenced by the shape of the confining boundaries. Okay. So a great variety of pressure sensors can be designed without the concern of the shapes as well as the dimensions. Okay. So when pressure is applied to one side of a surface enclosing a fluid or gas, it is transmitted uniformly across the entire surface without loss in the magnitude. The same example, if I see, I have this balloon where this fluid, maybe it's a liquid or consider it as a gas, I am calling it a fluid. Okay. So what I am trying to do is, I have confined this liquid inside this balloon. Means what I am doing is, I am allowing this liquid to exert pressure on the side wall of this balloon. So I cannot expect that if say for example this balloon is kept on a table, okay, consider two cases. In one case this balloon is kept on this table and in another case this balloon is hanging from the roof. Okay. I have trapped some liquid or say fluid in this. Okay. So, this is case 1, this is case 2. Okay. Now, if I am keeping it on this table, you cannot say that this liquid is exerting pressure only at this point. Or in this case also, if I have put this fluid, you cannot say that the pressure is being applied only at this point or say this point. Okay. So, whenever pressure is applied to one side of a surface enclosing this fluid, it is transmitted uniformly across the entire surface without any loss in the magnitude. So, pressure is applied to the entire surface of this balloon in both the cases. This is very, very important to understand the concept of pressure, which will help in designing and development of a pressure sensor. Okay. If I talk about gases, the kinetic theory of gases states that the pressure can be viewed as a measure of the total kinetic energy of the molecule which is acting on the surface together. Okay. So, pressure can be understood as from the equation, mathematically pressure can be given as 2 by 3 of kinetic energy by the volume. Okay. Or 1 by 3 of rho into c square, where c square is the average value of the square of the molecular velocities. Okay. And this of course is equal to nRT, where n is the number of molecules per unit volume. Okay. That n by v. Okay. R is the specific gas constant and T is the absolute temperature. Okay. The SI unit of pressure we all know that is Pascal. Okay. And 1 Pascal is defined as 1 Newton per meter square. Okay. So, if I define a Pascal is equal to 1 Newton of force uniformly distributed over a meter square of surface. Okay. So, please remember, I am telling it again and again because we are going to use that in the concept of designing the pressure sensors, that whenever you are talking in terms of force, please note that you should always recall the surface area where this force is applied. Otherwise, you will not be able to define a pressure sensor or the applied pressure. Okay. So, the definition of a Pascal is a pressure that is equal to 1 Newton of force which is uniformly distributed over a meter square of surface. Okay. Sometime in technical system we also use atmosphere or ATM as the unit of pressure, which is mostly denoted as say X amount of ATM. Okay. So, 1 atmosphere is the pressure exerted on 1 centimeter square by a column of water having a height of 10 meter at a temperature of 4 degrees Celsius and normal gravitational acceleration, by considering the normal acceleration due to gravity. Okay. So, definition of 1 ATM is very, very important, particularly if you are dealing with a technical systems which is denoting all the pressure in terms of ATM. Okay. A Pascal can be converted into other units because this conversion is important, because that is our SI unit, by the use of various relationships. Okay. So, if I talk about LB per inches, I can say that 1 Pascal is equal to 1.45 into 10 power minus 4 LB per square inch, and in ATM it is 9.869 into 10 power minus 6 ATM, and in the centimeter mercury scale it is 7.5 into 10 power minus 4. Okay. So, from these values it seems that 1 Pascal is actually quite a low amount of pressure. So, when you talk about high pressure, some other units has to be used. Okay. So, for practical calculation it is helpful to remember that approximately 0.1 mm of H2O is equal to 1 Pascal. Okay. So for industry application, there are another units of pressure which is mostly in terms of torr. Okay. So mostly the vacuum system that you will be dealing with if you go into deposition and other systems, the units are mostly in terms of torr. Okay. So the unit is named after Torricelli. Okay. So the unit torr is defined as pressure exerted by a mm of a column of mercury at 0 degrees Celsius at normal atmospheric pressure as well as at normal gravity. Okay. So one torr I can define from this definition as 1 mm of mercury. Okay. So the ideal pressure of the Earth's atmosphere is 760 torr or 760 mm of Hg and is called the physical atmosphere. So 1 atm can be defined as 760 torr or 101325 Pascal. Okay. So LB is per square inch also we have discussed. So some of the countries are still using that unit. Okay. Pound per square inch. Okay. Or PSI. Okay. So if I convert a PSI into SI system, 1 PSI is equal to 6.89 into 10 power 3 Pascal, which is of course our SI unit. This is also equal to 0.0703 atm. Okay. So I hope that we have understood different units of pressure. Okay. Let us now discuss the basic sensor or basic device that is used to detect pressure when you talk about some Pascal range. Okay. So a simple and efficient mercury pressure sensors is based on principle of communicating vessels. Okay. So initially most of the devices that were developed for detection of pressure was based on mercury pressure sensors, and these mercury pressure sensors have are actually based on the concept of communicating vessels. You can see this type of instrument is known as communicating vessel. You can see that there is a direct connection from the bottom of this say I am calling this first tube. Okay, and this is the second tube. Okay. So this is directly connected to second tube. Okay. Mostly this kind of setup is used to measure the pressure of gas, but of course it can also be extended in the measurement of pressure exerted by liquids. Okay. So if I talk basic mercury pressure sensor, usually a U-shaped wire is immersed into mercury that form two vertical columns. Just have a look on this U-shaped wire which is inserted into this U-shaped tube which is filled with mercury. Okay. So mercury is filled in this two arms of this U-shape. Okay. The mercury level shorts its resistance in proportion to the height of mercury in each column. Okay. So depending on the height of mercury column, the resistance will be shorted. Of course, this wire has some resistance, right? So if the column in this side of, I am calling it, say I am dividing it halfway. Okay. I am calling it side A1. I am calling this as side 2. Okay. I have divided this U-shaped tube in two parts. Okay. This is my side 1 and this is side 2. Okay. So depending on the rise of mercury, say if it increases in side 2, okay, so it means that it is going deep in this side, right? So it will shift somewhere here, okay, and this will rise somewhere here, and the difference between them I am calling it a delta R. Okay. So the mercury level shorts its resistance in proportion to the height of mercury in each column. Say if it is the mercury level has rose to this point, means till this point the resistance is shorted. Okay. Now these resistors are connected into a Wheatstone bridge configuration. You can see that this is connected to an amplifier through a Wheatstone bridge. This resistances makes the two different other arm of this Wheatstone bridge. So basically now you have the four arms of the Wheatstone bridge. Okay. So this bridge will remain in balance as long as the differential pressure in the tube is 0. Okay. When there is no differential pressure, the pressure is being applied from this point. Okay. If there is no differential pressure, means the output will remain 0. So basically this is a null type of device. Okay. So the bridge remain in balance as long as the differential pressure in the tube is 0. Okay. Now say some pressure is being applied to one of the arms of the tube. Okay. So now at this point it is in balance condition. Okay. So this, the ratio of the two arms is equal to ratio of the other two arms. That's how a Wheatstone bridge is balanced, right? So R1 by R2 is equal to R3 by R4, right? This is how a Wheatstone bridge is balanced. Okay. Now when you apply the pressure, there is a disbalance in the bridge because the other two arm resistance changes. Okay. When the bridge is disbalanced, there will be non-zero voltage. The voltage at the output is now not a zero value. It will read certain value. Okay. So the increased pressure in the left tube, okay, I am talking about this side 1. Okay. When you have increased the pressure, means the mercury level will go down here and it will rise this side. So that's how it is happening here. So the increased pressure in this left tube increases the resistance of the corresponding arm. Okay. When this level is going down, means that this wire is getting exposed, right? So when it was dip in mercury, means it was shorted. Now when you are dipping it, when this level has gone from the initial value, so when this liquid level goes down, this resistance is exposed now. Okay. So when it was dipped in the liquid, the resistance was low. Now when it is exposed, the resistance will increase. Okay. So the increasing pressure in the left tube is actually increasing the resistance of the corresponding arm. Okay. And the resistance of the opposite arm will decrease because when you are applying the pressure, this liquid is going up this side. Okay. Initially, say this length of this wire was exposed, right? Now this liquid level has rise to say this point, means this much more resistance has been immersed in the liquid or in the mercury. Because of that, the resistance of this portion will also drop, right? So what is happening is, due to increase in pressure in this side 1, I am calling it side 1 and side 2, you can also call it say left side tube or right tube. Alright. So due to the increase in pressure in this left tube, the resistance of the corresponding arm increases, the resistance of the opposite arm decreases with the same effect because of the applied pressure only. Okay. So the output voltage is proportional to the difference in the resistance. I am talking about this resistance of the wire arm, which are not shunted in the mercury, and this can be expressed at V out is equal to V into del R by R. Alright. So this is how a basic mercury pressure sensor work. Okay. And the sensors can directly be calibrated with the unit of torr because you are dealing with the atmospheric pressure and all. Okay. Although the configuration of this sensor looks very simple, okay, it is very easy to design. Okay, anyone can design this. Okay. However, this kind of device has several drawbacks. Okay. Please note that you require very precise leveling, particularly at the initial stage. When there is no pressure, you want your mercury columns to be at the same level so that the output of this amplifier is 0. Okay. So initially you require precision leveling of the two liquid meniscus. Okay. Then this is very much susceptible to shock and vibration because you are directly dealing with the liquid. Even a small shock in this or small vibration in this will have two effects. First is it will not allow the bridge to be at balance condition. Okay. So consider that this system is subjected to some kind of vibration. This vibration can be periodic, for example. Okay. There will be some output deflection between some plus to minus values, maybe in some nanovolt. Okay. But null condition will be very difficult to achieve. Okay. These devices are actually bulky in nature. They are very large in structure. When you are talking about CMOS integration of these sensors, it is very difficult, I mean nearly impossible. Okay. So when you are dealing with a very small quantity of applied pressure, this kind of devices are nullified. Okay. So then there is another point which we have to take into consideration is the how you are applying the pressure. Okay. So if this pressure, usually this pressure is applied using some gas. Okay. So usually to calculate the pressure of the gas, this kind of structure is used. Okay. Now if this gas can dissolve in mercury or if it can react with mercury, okay, by any mean it can contaminate this liquid. Okay. There is another chance that gas can also be contaminated using this mercury. Okay. So say this gas molecules are coming to exert the pressure on this mercury column. However, some mercury fumes are already there and it acts as a carrier gas, So it takes this, say there are 3 Hg molecules and say 20 nitrogen molecules is coming, and we are trying to find the pressure exerted by this 20 nitrogen molecule. What it will do is, it will, while coming back, it will take these 3 Hg molecules also. Okay. So now you wanted to calculate the pressure applied or pressure exerted by this 20 nitrogen molecule. Now at the end what you are getting is pressure applied by 20 nitrogen molecule plus 3 mercury molecules. So altogether 23 molecules. Okay, of course 20 from nitrogen and 3 from mercury. So it may not give you the correct data. Okay, so there is a chance of contamination of the mercury as well as contamination of the gas by mercury. Okay. So therefore various other precise pressure sensors has been proposed over the time, particularly based on MEMS technology. Okay. Most of the devices are either diaphragm based or plate based or membrane based, and they deform under the applied pressure. There can be multiple transduction phenomena like piezoresistive, capacitive, piezoelectric, opticals and so on. Okay. But the element remains similar. Either it be diaphragm or it be a plate kind of structure, or sometime it can be simple membrane also. Okay. However, the transduction technique can vary. Okay. So what we will do is, we will discuss in our 4th lecture some of the modern pressure sensors based on these sensing elements. Thank you.